PhD advisor, Jared Speck. Okay, so the plan for this talk, first of all, I will introduce what is the 3D compressible Euler equations. Then, because I need to tell you what is the characteristic initial value problem, so I have to tell you what are the characteristics. So that involves a new formulation of the compressible Euler equations. And then I will introduce the characteristic initial value problem. Okay, so the problem mainly I will focus on two parts. The first part is how we construct the initial data. The second part is how we get our main result, basically the local well-posedness in the neighborhood of initial hypersurface, and the continuation criterion and the regularity theory. Okay, so that's basically the plan. So let's dive into the compressible Euler equations right away. So the fundamental PDEs in my consideration are velocity v and log density rho. So I use log density just for simplicity in computation, and I assume there is a background density rho bar, which is a positive constant. So basically, I assume a background density to avoid the degeneracy of the Euler equations. And then lastly, the last fundamental PD variable for in my PD is entropy S. Okay, so in this setting, you will have more variables than equations, so you need an extra assumption on pressure, which people call equation state, where pressure P is a function of density and entropy. Okay, and the speed sound is defined in this standard way. And B is a material derivative. I'm abusing the notation so that such thing like B can stand for a operator, derivative operator, but can also stand for a vector field on spacetime. Okay, so in this regard, in this setting, I can formulate the first order compressible Euler equations in the following form. So at this point, you don't need to pay too much attention to the details, but this will be very useful and very intensively used once we construct the initial data. Okay, so for now, for simplicity, we'll just write the compressible Euler equation in the following schematic form. Okay, so I may say a lot of word like solutions. So by solution, I mean psi. So psi simply means the components of V, rho, and entropy S. Okay. Now, unfortunately, I cannot tell you what is the characteristic in IVP right away because I have to tell you what are the characteristics, but that requires some background. So maybe I should start with the standard initial value problems. So basically, consider a smooth solution to the compressible Euler equations in multiple space dimensions, whose initial data on the initial Cauchy hypersurface, which I denote by sigma 0. Okay, then various results, and many people work on this on this problem and has many phenomenal results. Unfortunately, I cannot list every one of them. Also, I will just list mostly the most recent results and the results that inspires our work the most. So the study of compressible Euler equations in 1D, you can trace back at least as early as 3 months, and for the 3D problems, you can trace back to as early as Fritz-John. So you will have, first of all, you will have local well-posedness. If you want to consider long-time behavior, which is apparently more interesting at this moment, Chris Dulu, in his monograph, Breakthrough in 2007, suggests that even for very small data, you will have a shock formation. You can have a shock formation in finite time. Okay, so Chris Dulu did it for the irrotational isentropic relativistic Euler. So there is a special property about the Euler equations is that if initially the system is irrotational and isentropic, it will remain so until the singularity forms. Okay, and the relativistic Euler equations is just compressible Euler equations in the settings of special relativity. Okay, so Christoulou's result was extended by Luke Speck and Speck himself with dynamic vorticity and entropy. Okay. And there is a different group, Buckmaster, Scholar, and Bickel, using a different method, also derive the shock formation. And there is another type of singularity, which is called unstable implosion. So this is called if you have a special initial data, you will have density blow up, and this singularity is conjectured to be unstable. So compared to the shock formation, where you have solution itself remain bounded while the certain direction or first derivative blows up. Okay, so shock formation connect closely to the collider of the characteristics. So those results, all of these results are from standard initial value problem. However, local well-posedness theory for the characteristic initial value problem for 3D compressible Euler is not established. Okay. So in order to tell you what are the characteristics, I need to tell you I will introduce you a very important concept, which is called acoustical metric. All right. So first of all, G is a Lorentzian metric and depends on all three of the solutions. So basically, C, speed of sound, depends on density and entropy, and B, and here you will have you will know that the metric depends on the velocity as well. So this is this is the metric which governs the wave equation, quasi-linear wave equations derived directly from the first order Euler, and it governs the sound waves. Basically, we will construct its characteristics, which is the hypersurface that sound travels. Okay. So the other important property that I should mention is the material derivative B is transversal to any G null hypersurfaces. Moreover, this material derivative B is time-like, and that means in the point of view of material derivative, the null hypersurface has no too much difference than any space-like hypersurfaces, which is a very important, which allows us to derive good enough elliptic estimates and energy estimates to close the argument. Okay, so you will see in 1 second what do I mean by what do I mean by these geometric quantities. All right, so now I can introduce you the geometric formulation for the 3D compressible Euler equations. So it consists of 2 slides. So in this part is so-called wave part. They consist of quasi-linear wave equations of the fluid variables. And again, G is a solution-dependent Lorentzian metric. Okay, so C is the vorticity of vorticity, and D is the Laplacian of entropy. If you compute, well, if you just count the derivative of equation 4, you will have two derivative of solution on the left and 2 derivative of solutions on the right. Okay, so that will not give you anything if you don't have extra property for C and D. So luckily, it turns out that we have. So if you look at the equation 7, that basically tells you that C and D satisfy a good transport deep closed system. So you need a deep closed system for vorticity and entropy gradient to close the argument, but this is not the main point that I want to talk about today. So what I want to tell you is there are, for the Euler equations, there are 2 types of characteristics. The first type of characteristic are wave characteristics, which is the standard characteristic in wave equations. There are null hypersurfaces. And the second type of the characteristics are the characteristics by flow itself. So basically, the integral curve led by the material derivative. All right. So for our problem, characteristic IVP, we impose our initial data on the wave characteristics. Basically, we post our initial data on null cones. Okay. So how we impose them is a big question, and I will show you maybe in 5 slides. But as for now, let's just get an understand of what is the characteristics, what are the characteristics in this problem. So if you look at this picture, we have this blue line, which we denote by H ring, is a outgoing null hypersurfaces. So this is the outgoing initial null hypersurfaces, which we are going to impose our data on. And also we have another incoming null hypersurface, which we denote by H bar ring. Okay? And we will post the initial data on H bar and on H, and we try to consider the solution in this characteristic diamond. All right. And there are level set of U and U bar, and U and U bar actually solves the iconal equations. In linear case, you can think U is close to T minus R plus 1, and U bar is close to T plus R minus 1. All right, so here my blue line is curved because, again, the metric depends on the solution. So the characteristics is curved because it depends on the solution as well. And moreover, the intersection between H and H bar denoted by SU bar, which are two spheres. I'm compressing one dimension here, so you see circles, but it actually should be spheres. All right. So now, before I dive into the details about how I set up the problem and how I solve the problem, I want to tell you why I want to solve or why I want to study characteristic IVP. So the first reason is seen in Einstein equations, 1D Euler, but not for 3D Euler, unfortunately, is that sometimes it's easier to imply favorable assumptions on initial data. So for Einstein equations, in the monograph by Chris Dulu, he proved the formation of trap surfaces by implying some short pulse data, which is more convenient when you apply this strategy on null hypersurfaces. For Einstein equations, if you want to post initial data on space-like hypersurfaces, you need to solve a scary constraints equation. But if you want to post the initial data on null hypersurfaces, it looks easier because everything can be transported. Okay. However, unfortunately, this is not the case for the 3D Euler case. All right. So one of the main reasons that we want to study characteristic initial value problem is due to the boundary of classical existence. In particular, as I just showed you earlier, for data small enough, you will have shock formation. Even for data small enough, you will have a shock formation. All right, so then you want to ask yourself, how can I continue the solution after the shock? Well, before that, you need to first answer what's the maximum region in spacetime that the strong solution exists. So your maximum region of strong solution consists of two parts. The first part is bounded above by a so-called shock hypersurface, where the first derivative of the solution blows up. It's a space-like hypersurface. And the other part is so-called Cauchy horizon, which is a null hypersurfaces, which is an incoming null hypersurfaces starting from the initial shock point. And you cannot uniquely continue the solution across Cauchy horizon because the Cauchy horizon is due, you lost the information due to the initial shock along Cauchy horizon, so that you cannot continue the solution uniquely. Okay, so in this setting, if you want to post initial data on space like hypersurface, you will have boundaries, or in other words, you might have shocks on your initial data hypersurfaces. That can be troublesome if you do not be careful enough. So instead, you can to overcome this problem, overcome this issue, you can solve acoustical quantities, U and U bar, is just like the iconal optical functions in relativity. So you solve acoustical functions backwards a little bit, and you construct a characteristic initial value problem, and you try to solve the characteristic initial value problem near the Cauchy horizon. Okay. So the boundary of classical existence, the issue of the boundary of classical existence also exists in the region of relativity. So if you only want to consider the data in the interior region, well, you might as well consider the characteristic initial value problem. Okay, so so that's the second point of the motivation. The third point is required by the physical nature. So again, if I have already constructed the maximal development of the strong solution, then I want to ask, how can I continue the solution weakly? That is called the shock development problem. So shock development problem is a characteristic boundary value problem. So basically, it means on one side, you have a characteristic data. On the other side, you will have a boundary value data. Okay, so Christodoulou in 2019 solved a restricted shock formation. So he manually set the entropy to be 0 after the jump. So it's non-physical, but it's still a breakthrough result. All right, so any questions before I dive into the details of characteristic IVP? All right. Now let me spend maybe 3 slides talking about how people did to have a local well-posedness result for characteristic IVP in different regimes. All right. So the first fundamental result was by Randall. Given the initial data on H and H bar, he proved the local well-posedness result in a neighborhood of initial sphere. All right. So the method he used is very inspiring. He turned the characteristic initial value problem into a standard Cauchy problem. So he find initial data set on a space like hypersurface such that the evolution agrees with the evolution of the characteristic initial value problem. So by the standard theory, he can have a local well-posedness in a neighborhood of initial sphere. All right. Then Randall's result was extended by Jonathan Luke maybe 11 years ago. Well, Luke shows that you don't not only have well-posedness in a neighborhood of initial sphere, you actually have well-posedness in a neighborhood of initial hypersurfaces. Okay. So I prefer to call it a characteristic Nike. So he showed that the solution is locally well-posed in such characteristic Nike. And moreover, he gave a regularity theory saying that if the solution is H4, if the data is H5, then the solution is H4. All right. And in our work, we will give a regularity theory as well, but in this regard, we will be careful about what do I mean by Sobolev regularities. Okay, that's just a heads up. So both Randolph's result and the Luke's result are mainly focused on the Einstein equations, but what about the compressible Euler equations? Or so unfortunately, there are no results till now for 3D compressible Euler equations without any symmetry assumptions. But if you impose spherical symmetry assumption, you actually, Andre Lisabach showed that, first of all, he construct the initial data together with the initial geometric coordinates. Then he proved the local well-posedness result in a neighborhood of initial hypersurfaces. So what Lisabach tells us is the initial data cannot exist alone. It must be constructed together with the geometric coordinates. Basically, you should construct solution. So you need to construct data v rho s together with u and u bar. Okay. So this is the main difference between the case in relativity and in compressible Euler. So in compressible Euler, you always have a God-given Cartesian coordinates. No matter what the geometric structure you consider, you always want to link back to the original Cartesian coordinates that God gives you. Okay. So basically, in other words, you always want to consider the change of variable map between the Cartesian coordinates and the geometric coordinates. And this problem existed in the level of initial data because you have to construct your geometric coordinates together with the solution because the characteristic depends on the solution. All right. So so the difficulties of the characteristic IVP in 3D mainly consist of following two aspects. The first one is it's really hard to construct initial data. First of all, initial data and the initial hypersurfaces are deeply coupled, and we are unable to solve data as solutions of transport equations. Okay, so in the spherical symmetry case, because of the existence of Riemann invariant, you can actually solve Riemann invariant together with the geometric coordinates by solving transport equations. Well, that is not the case in 3D without symmetry. Okay. Then, unlike the standard Cauchy problem, so in standard Cauchy problem for compressible Euler, you can prescribe the initial data freely on initial hypersurfaces. However, in characteristic IVP, you are not allowed to do so because, first of all, the solution, the initial data you constructed will be such that, first of all, your initial hypersurface is a null hypersurface, and second of all, your initial data must satisfy the Euler equation. And you cannot get these two conditions for free. You have to construct the data such that they are satisfied. Okay, so that divides your initial data into two parts. The first part is the free component, which basically means you can prescribe them on the initial hypersurface freely. And second part is so-called constraint part. You have to solve it by using the Euler equation and the free component, which I will provide detail next slides. Okay, once we have initial data constructed, well, now we have formulate our characteristic IVP. So to find any local well-posedness result, it is there are extra components that you need to consider because the compressible Euler with dynamic vorticity and entropy is a multi-speed problem. Basically, vorticity and entropy gradient will satisfy transport equation while fluid variable satisfy wave equations. So that basically means when you try to do energy estimates for your transport part, you will encounter boundary terms because you are working things in a characteristic diamond. which is very different from the standard Cauchy problem. And you need to get a precise control and understanding about those boundary components. All right, so so that's a little bit of heads up of the difficulties that we have for characteristic IVP for 3D Euler. So at this stage, I think it's a good time to start to investigate into the initial data set. Okay, so I want to use this example. So again, this is not the Euler equations, but this is just the standard linear wave equations, but it gives a rich insight of what we have to do if we want to pose the initial data on characteristic hypersurfaces. Okay, so let's consider this standard linear wave equations. Okay, and if you write in the geometric coordinates, it is written as equation 8, L over L bar psi plus this is angular Laplacian psi plus lower order terms. Okay, so because it's a linear wave equation, so L is just dt plus dr, and L bar is dt minus dr. All right, so here is what we're gonna do. So we prescribe freely psi on initial hypersurface H and H bar. All right, so let me for now just consider the initial data on H. So once I prescribe initial data psi on H, okay, so first of all, L is a null generator of H. Well, once I prescribe data on H, it is worth noting that tangential derivatives of psi at all orders are already prescribed. Okay, because I'm prescribing data on null hypersurfaces. So in other words, L psi angular derivative of psi is determined already. Okay, so what remains to be done is solving the transversal derivatives along the null hypersurfaces. Okay, so basically in this regime, you can say psi itself is a free component of the data, and the transversal derivative is a constraint component of the data. So you have to solve. So the transversal derivative of psi cannot be prescribed freely. It must satisfy this equation, wave equation 8. Okay, and you have to solve it along the integral curve of L. All right. So there are two things that you need to pay attention in this process. The first of all, L bar psi will have one less regularity than the angle than the tangential derivatives, because if you want to solve A along the integral curve of L bar psi, it depends on the two tangential derivatives of psi. So basically, L bar psi, you lost one derivative by solving this wave equation for L bar psi. Okay, so that's the first thing. That is, you have loss of regularity, loss of derivatives at the level of initial data set. Okay, for the simplest linear wave equation, even. All right, so that's the first thing. The second thing is when you solve for L bar psi, you cannot solve for L bar psi directly because L bar psi is not well defined. Remember, you only prescribe psi on initial hypersurfaces. So basically you don't have any psi inside your characteristic diamond. So basically L bar psi is not well defined. So what you actually solve is a candidate of L bar psi, or the seeds that you want to use in your Whitney extension. Okay, that's another technical part that you need to pay attention. So basically, you just solve for the candidate of the transversal derivative of the solution, but not the transversal derivative solution itself directly. Okay. However, this is already giving a rich insights of what's going to happen if you post characteristic initial value on initial hypersurfaces. But the reality in compressible Euler is much more complicated due to nonlinearity and multi-speed phenomena. Okay. So so basically, there are many aspects that I can talk about for the initial data. So first of all, the free data are not free. So unlike the linear wave that you can freely prescribe psi on initial hypersurface, you can't in the settings of 3D compressible Euler. So basically, you want to prescribe solution. You want to prescribe fluid variables V, rho, S on initial hypersurface in certain order or in certain such that they satisfy the Euler's equation. Okay. So this proposition tells you what are the legitimate initial data you want to put in. So so first of all, initial data. So initial hypersurface should be a part of the initial data. So basically, you cannot have a initial hypersurface just standing there before you prescribe any initial data, because initial hypersurfaces depend on the initial data. But you cannot just say you cannot construct it. You cannot construct such initial hypersurface without knowing the data. So basically, because they are deeply coupled, so you have to construct them in one go. So to deal with this problem, we assume that the initial hypersurface is a part of the data. We realize that by using the function which we call the initial embedding functions. So which I will show you in the next slide. All right. So the free components of initial data for characteristic IVP for 3D compressible Euler equations are a pair of transversally intersecting null hypersurfaces embedded in a Cartesian spacetime, and fluid data are prescribed on H and H bar. Okay. So in this process, fluid data and the embedding are prescribed such that they satisfy the following two properties. First one is the initial hypersurface are null with respect to the acoustical metric. The second property is the fluid data on H and H bar satisfy Euler's constraints. So Euler's constraints equation is just the Euler first order Euler equations restricted on the initial hypersurfaces. Okay, so whether people can solve these two properties remains unknown. We don't know yet. So let me show you what are these two properties actually means. So, okay, so I only consider the outgoing hypersurfaces H. So, equation 9, equation 9 just means the initial hypersurfaces. Initial hypersurface is null. Okay, so first of all, I is the embedding that maps a flat cone to a geometric cone embedded in Cartesian spacetime. Okay, so you should view like di over du bar as null generator L or E4 for different normalizations, and you should view di over d theta to be derivatives or vector fields on spheres in the on two sphere SU bar. Okay, so basically the equation 9a tells you g of LL is 0. The second equation 9b tells you that g of L comma EA is 0. So basically the first one is the tells you that you have a null generator. The second one is the orthogonality for your null generator and the two sphere. Okay, and the equation 10 is so-called the Euler constraints equation. they are it is the compressible Euler equations restricted on H. So E4 EIs are principal null pair normalized such that G of E4 E3 is -2. All right, and those slashes are projections on two spheres. So basically, for example, B slash is projection of B onto the two sphere. Okay, so basically, if you look at equation, all the terms in equation 10, except the last term, every term is in terms of tangential derivatives of the data. So basically, your data must satisfy this, so that your data actually satisfy Euler's equation on initial hypersurfaces. Okay. And for the last term, you can actually write it in terms of tangential derivatives as well, because material derivative B act on entropy S is 0. Okay. So so these are the initial data assumptions. So again, we don't know yet if this can be solved. Basically, we don't know if I and rho vs can be solved starting from the initial sphere. So at this point, we just assume this holds, and this is a very general setting. So basically, we will prescribe rho vs on initial hypersurface as long as these three equations are satisfied. Okay, and you can find this. You can find these three conditions satisfied everywhere in the standard Cauchy evolution problem. Okay, so assuming the initial data and the embedding satisfy the previous conditions that we listed, we can construct the initial data as follows. So again, once I have VROS prescribed, I have every tangential derivative prescribed. Okay, so that basically what's remain to solve is transversal derivatives. So that goes back to the case we discussed for the linear wave equations, but the order matters. So basically, you have to solve VROS in a special order, such that you can construct Whitney extension seeds for transversal derivatives, and in particular for C and D. So C again is a vorticity of vorticity, and D is the Laplacian of entropy gradient. Sorry, Laplacian of entropy. Both of C and D contains transversal derivatives. Okay. So again, the order matters, but I don't want to dive into details. Then once we have constructed Whitney seeds, then we can Whitney extension. We can use Whitney extension theorem so that the initial data that we constructed is actually well defined in the transversal direction. Okay, then we can use Randall's method to obtain the local existence in a neighborhood of S00. So actually more details, you will need more details than Randall's method. Because the solution, sorry, the data you constructed, you need to verify that the initial data that you constructed satisfies compressible Euler in every order. So basically, equation 11 need to be satisfied for your Whitney extended initial data. Okay. All right. So any question for now in terms of regarding the construction of initial data?
All good, all good.
Okay. Nice. All right. So once I have my once I have constructed my initial data, what can I do about that? Okay. So roughly speaking, I can derive a local well-posedness result in a neighborhood of initial hypersurface. Secondly, I can derive a continuation criterion saying that in what condition I can continue the solution beyond. Lastly, I can give a description of regularity behaves. So first of all, this is the general case. So we will have a special case in the next slide. I will tell you the difference between general case and a special case. So let me remind you that we will, even for the linear wave equations, we will have loss of regularity in the transversal part, transversal derivative. So general case is coming up to deal with that thing. So given the data above, you know that the transversal derivative behaves much worse than the tangential derivative. So basically, we show that the solution is well posed in a neighborhood of initial hypersurfaces. So basically, well posed in the characteristic Nike, same as what Luke did. Moreover, the Sobolev regularity can be propagated in such way. So, so basically, so I refuse to use Sobolev regularity here because Sobolev regularity is not well defined, as you can see, because it's, oh well, you can define it in your own way, but here I kind of want to only use this notation. So if my data is partial bar n, so basically that means I can take n tangential derivative on my initial data. So by the loss of regularity that we investigated just earlier, we have the result that we can only take n over 2 transversal derivative of the data, right? So basically, you take one transversal derivative, you lost one derivative. Okay, so basically, so that's why if your data is, you can take, so basically that means if you can take n times, if you can take n tangential derivative of your initial data, you can only take n over 2 tangential derivatives of your initial data. So since initially you lost regularity, so that's basically what you can hope for the best. So due to the multi-speed issue, you lost more regularity upon the process. So basically, at the end of the day, if you can take n derivative of your initial data, you will only have 0 as leaving Sobolev space H to the n minus 1 over 2. Okay. So in particular number that might interest you is that if n is 9, then V rho S are in H4. And in such way, you can close the argument by bootstrap assumptions. Okay, so that's the general case when you suffer a loss of regularity at the level of the initial data set. All right, so but that's not always the case in the physical world, right? So in practice, especially in constructing the maximal development of the strong solution, you don't have such loss of regularity. Okay, so that loss of regularity just caused by maybe a bad construction of the initial data, or by the nature of construction of the initial data. Okay, so we consider a special case. So basically, here's what we're gonna do. Assume on H bar, there is no loss of derivative in initial fluid data. So this might be a little bit confusing. So so the transversal derivative on H bar is L direction, so or the E4 direction. So I'm assuming E4 of psi is as good as E3 psi EA psi on H bar. Okay. So what I want to do is I have my data and I assume that my L direction of data is always better. Okay. L direction of the data don't have loss of regularity on the incoming non-hypersurfaces. Then I can propagate my regularity as well. So that is something worth mentioning because, you know, in this setting, E3 of psi is a transversal derivative on H, which you lost derivative in the level of initial data. So, but I can still propagate the regularity of E4 psi and E8 psi, despite that E3 psi is less regular. So, in particular, if I have if my initial data, if I can take n tangential derivative of my initial data, plus the assumption that I can take n times n E4 derivative on H bar, then I can have my solution in Sobolev space H to the n minus 3. So compared to the previous solution, it is much better because you remove the denominator 2 here. Okay. Okay. So basically, this theorem tells you that even though some direction of derivatives of the solution is bad, you can still propagate the rest of the derivatives of the solution. So that's very close to what happens in the shock formation. All right. So so I will briefly give a sketch of the proof because I'm running out of time. So I think I mentioned the first step at the end of the construction of initial data. That is, we apply a Randall's method, but it's actually much more complicated than what Randall's did. To construct a well-posedness in a neighborhood of initial sphere. Okay. Then we want to extend the existence region to a characteristic Nike. Well, the ingredient we need, first of all, very important, is a priori estimates, which consists of energy estimates and elliptic estimates. So the elliptic estimates also, first of all, energy estimate consists of energy estimates for wave equations and the transport equations. And the elliptic estimates is to deal with the vorticity and the entropy gradient part. Okay, and this is not easy because now you are in double null foliation. You are basically you don't have constant time hypersurfaces anymore. Basically, you have a constant tau hypersurface where tau is the u plus u bar. Okay. So you want to do elliptic estimates on a geometric space-like hypersurface, or you want to do elliptic estimates on a space-time region with boundaries. And this is very non-trivial. And luckily, we have the work from Abresha and Speck. They give a description, or they give a space-time elliptic estimates such that it is compatible with the work we are working on now. All right. And once we have those energy estimates, we can use both standard Cauchy evolution and the Randall's method for characteristic initial value problem to extend the region, which I will show you in the next slides. Regarding propagate the regularity, so I'm talking about the special case where you can propagate better regularity despite some direction is worse. This is due to the commute geometric wave equation with null frame as follows. So basically, if you commute your geometric wave equation with your null frame, you will not have the special case. You will have at most one more transversal derivative. So basically, if I commute with E4 or L, or and the spherical derivatives, I will not pick two L bar derivatives. Okay, so that's important. And one E3 or one L bar derivative is acceptable because of the energy estimates. All right. So this is the main ingredient, or this is the main observation that people needed for propagate regularity in the special case. Okay. So let me tell you how to extend the random region to the characteristic Nike. So this picture is a little bit too much, but I will try to explain from in details. So assume M0 is the maximum region you have for your well-posedness in Randall's theorem. Okay, so assume M0 is maximum region, and assume you have every ingredient you have on the whole spacetime, every priori estimates in the region, at least the drawing here. Okay, then the plan is I want to extend M0 to a bigger diamond, so that will contradict to what I just assumed. Okay, so first of all, I will use Randall's method to extend the region of existence to M1. Okay, and it is worth mentioning that you cannot repeat Randall's regions again and again, because this square might shrinking every time you use Randall's method. So you cannot hope you just use Randall's method to cover the whole region M2. Okay, so once I have M0 and M1, I have a space-like hypersurface which I use a green line, so that I can use standard Cauchy evolution, such that I can get a well-posedness on this triangle, right? Then I can have another space-like hypersurface that allows me to continue my standard Cauchy evolution until I cover the full region of M2. Okay, then since I have covered M1 and M2, I can repeat the same process on the other side for M3 as well. So in that regard, I get a bigger diamond that contradicts to the assumption that M0 is the maximum diamond of the existence and the uniqueness of solution. Okay, so let me skip the continuation criteria and jump to the open problems. Okay, so there are many problems remain to be solved. So first of all, there definitely will be a parallel development for the relativistic Euler equations. So for basically the characteristic initial value problem for 3D relativistic Euler without any symmetry assumptions. And second topic is about is there an analogy of trapped surface in compressible Euler? I don't know. My opinion towards negativity, I didn't find any monotonicity argument in the regime of compressible Euler. As for now, all right. The third topic is the characteristic initial value problem for other hyperbolic systems. For example, Einstein-Euler or elastic waves. That will be very interesting. And then more understandings of the initial data, which I mentioned earlier, we are not able to solve, or maybe it's not solvable. We are not able to solve the initial assumptions. We are not able to solve the assumptions for our initial data and the initial embeddings, and that problem looks very hard because we don't even know the type of the equation yet. All right, the last open problem I list here is the long-time dynamics. So basically there are many aspects. One of the aspects is the change of variable map. Remember, you always want to transfer your geometric structure back to the Cartesian coordinates. So you want your change of variable map still to be 101. Right? So in reality, you will have some pinch-off properties. So basically, your sphere will pinch off after during your evolution. So basically, you have to control the injectivity radius, which is very hard to be done in the regime of compressible Euler. Okay, so I think I should stop here, and thank you for your attention. Okay, so I see one question already. Yes, sure, I can get I can send this to chat. Sure.
All right, let's thank Sifan for this wonderful talk. Very interesting. And if anybody has any questions from the audience, please unmute yourself and go ahead and ask. Do you have any questions from the audience?
Maybe you could, first of all, amazing talk, congratulations. Maybe you could cover a little bit of the continuation criteria that you skipped.
Oh yeah, that's right. So the strategy in the continuation criteria is pretty similar to the local well-posedness. So I assume the following four conditions so that I can continue my solution. So first of all, the solution is well-posed in a smaller diamond.
Mm-hmm.
Secondly, I have finite energy on the boundary of my smaller diamond. Okay. Secondly, I have L infinity bound on my boundary of my smaller diamond. Okay, so I need to mention that omega, mu, and mu bar are null lapses. So we have three lapses because if you in GR you will only have omega that measures the closeness between U and U bar, but you also need the mu and mu bar. We call inverse foliation density that helps you to measure the difference between U and U bar to the Cartesian spacetime T, Cartesian spacetime. So basically, mu is 1 over BU, and the mu bar is 1 over BU bar. B is a material derivative. So in our work, you need three lapses. Okay, so the last one is the most important one that I mentioned before. So you need your change variable map to be C1 diffeomorphism. Okay, so you can only get a local result based on your estimates, but it is unknown yet if you can get a global result, a global control over the change of variable map, or a global control over the injectivity radius, such that your sphere is well behaved all the way in your diamond. This is hard, maybe, or you can prove a counterexample to that. Okay, so if these four conditions satisfied, then the solution can be uniquely extended to a bigger diamond. So this is so-called the continuation criteria in our work.
Mm-hmm. Thank you so much.
Yeah,
great
thank
talk.
You.
Great talk.
Hi, Sifan. So I want to ask you this. So I understand, like, you have this loss of regularity problem in characteristic initial value problem in general.
Yes.
Like for the GR, I understand if you have some HN, you get HN minus 1. So, but here I couldn't actually understand like the argument that you were like the logic that you actually said. Can you actually repeat that, please? I was, maybe
Yes.
I wasn't paying attention. Yeah.
Yes. So first of all, for consider the linear wave equations, I prescribe psi on H freely, so that the tangential derivative of psi is understood. And then I want to solve the transversal derivative. So the transversal derivative is not free because it must obey these linear wave equations. So I solve the transversal derivative, which I denote by L bar psi, by this transport equation, lead by L. However, if I solve L bar of psi in this way, L bar of psi will depend on the angular Laplacian of psi. That means the transversal derivative has one derivative less regular than the tangential derivative. Okay, that's where the loss of derivative comes from.
Yes, yes, and if you go back to like a couple of slides later, like when you have
this one or this
a little later, so yeah, here. So this is just counting, right? This is just derivative counting.
Yeah.
This n to n minus 1 by 2.
That's right. Yes. So basically, in general, if this is a single speed problem, you will have V low s leaving h of h to the n over 2. But it is a multi-speed problem. You also need to take into the transport part into account. So we actually lose more.
I see. Okay. Yeah. Right. Yeah. Okay. Thank you. That makes sense. Yeah. Yeah. I was wondering about this n minus 1 part. So n minus 1 by 2. So n by 2 minus half. So this is basically happens because you have this.
So basically, you also need to compute the C and D. C is the vorticity of vorticity, and D is the Laplacian of entropy. So you need to construct it as well. So you lose more derivative in that process.
Right. So in that case, like your vorticity is actually transported by the flow. So you have different speed. That's okay. So you have two speeds basically, right? One is the sound speed, one is the actual flow velocity.
Yeah.
Okay, that makes sense. Yeah, that makes so much sense. Thank you. Yeah.
Cool. All right. Any other questions?
All right. So if we don't have any more questions from the audience,